Okay, so our next speaker is Isabella Negrini, who will be talking on a Shintani map for rigid cocycles.
Okay, so thank you for the invitation. I'm going to start with a short introduction on rigid cocycles. So these objects were defined, they were introduced in 2017 by Darmon and Vonk with the idea of extending complex multiplication theory to at least real quadratic fields. And we will define them more precisely later in the talk. But for now, you can think that they are objects living on the p-adic upper half plane, which is HP here, and it is defined as P1 of CP minus P1 of QP. Okay, so on this p-adic upper half plane, there are certain points called the real multiplication points. So a point tau on HP is an Rn point if Q of tau is a real quadratic field. And so Darmon and Vonk, they defined how you can evaluate certain rigid meromorphic cocycles at these Rn points. And then they computed these values, and they conjectured that these values belong to narrow ring-class fields of real quadratic fields. And so this is why they are said to be analogs, real quadratic analogs for singular moduli, because singular moduli are the values of the J function at complex multiplication points on the usual upper half plane. And then these singular moduli, they generate the Hilbert class field of imaginary quadratic fields. And so this is why we say, so because of the conjecture of Darmon and Vonk, this is why we say that the Rm values of rigid cocycles are analogs of singular moduli. So I also want to mention that this year, a year ago, there was a new paper appearing in which Darmon, German, and Lipnowski defined some generalizations for rigid cocycles. They defined the rigid cocycles for orthogonal groups. So given a quadratic space of signature Rs, they define certain rigid cocycles, and the original picture would be a special case of the new one for signature to 1. And in this paper, they initiate the so-called p-adic Kudla program, which has 2 aspects. So one is building modular generating series from rigid cocycles, and also the second aspect is evaluating these cocycles at certain points. And the work that I'm presenting today, well, the work that I present today is about the original cocycles, so the ones for signature to 1. And it fits into this picture of building modular forms, because we'll see that we will build the modular forms from its coefficients. And so now I wanted to give some background and mention some works in this p-adic Kudla program. So the first one is a work by Darmon and Vonk, which is an analog of something that was previously done by Borchers. So let's say at first what Borchers did is he associated to phi a nearly holomorphic modular form of half integral weight. He associated to this a certain real analytic function having singularities at CM points, and they are determined by the principal part of the starting object. And then Darmon and Vonk, again, they start with a similar object, so again, nearly holomorphic modular form of half integral weight. Now there's a P in the level. And they define now a rigid cocycle, which now has singularities at real multiplication points. So these are now in the p-adic upper half plane. And again, these singularities are determined by the principal part of the starting object. Okay, so now I want to mention another work, which is an analog of the Shimura lift. So at first I'm going to present the classical Shimura lift and then the work in the setting of rigid cocycles. So the Shimura lift goes from half integral weight modular forms. So K here is an integer. 2 integral weight modular forms. And it is given by a certain theta kernel function. And in the next slide, we're going to see what do we mean that when we say that it's given by this, okay? So how can you use this to define the map? But anyway, this thing is a function of 2 variables in the usual upper half plane. And so this is a Q series, and the coefficients, these FKDs, these are modular forms here. They have integral weight. So these are functions in this space. So they have integral weight. We also call them the Zagier forms. And if you fix Z, then this object for Q becomes a modular form of half integral weight. So here. And so what we say is that this is a half integral weight modular form with coefficients in integral weight modular forms. And another way to say this is that this omega k belongs to the tensor space of the first, so the half integral and the integral, okay? So the first space and the second space. And we will use this expression given as the tensor product in the next slide. And then similarly, so in my PhD thesis, I defined a map from half integral weight modular forms to rigid analytic cocycles. I will define these cocycles later in the talk. And again, the definition uses a function of 2 variables where now Z is in the p-adic upper half plane. And now these coefficients are, for Z, they are rigid analytic cocycles. So before we had these Zagier forms, which were modular forms, and now we have rigid cocycles. And so we say that, so this omega hat is in the tensor product of half integral weight forms and rigid analytic cocycles. And this is what we mean when we say that it is a half integral weight form for Q with coefficients in the rigid analytic cocycles. We mean that it is in the tensor product. So now I'll show how we can use omega or omega hat to define the Shimura or the rigid Shimura lift. So normally we see the expression that we see, so for the Shimura lift is the following. You pair with the Peterson inner product, you pair the kernel function omega k with G. So let's say G is a half integral weight form and you want to compute Shimura of G, and then you pair G with omega. Because for tau, both G and omega have half integral weight, so this integral kills tau, then you're left with Z, and so you're left with integral. But this expression is not, well, it's not ideal to generalize it to rigid cocycles, so I'm going to give an alternate expression. So you can rewrite this thing if you take a basis for the starting space, okay? So these are the half integral forms. And well, then remember we said that omega k was in the tensor product of half integral and integral forms. So it will be a finite sum, and then you have the basis for the half integral weight forms, tensor some elements here, some forms of integral weight. Okay, so for sure we can have this finite sum. And so then that's how we can define the Shimura lift. If you want to do Shimura of G, and G has half integral weight, okay, then you write G with its coordinates on the basis. So these are just scalars, and you write it on the basis, and then you send this to, and now you multiply the coordinates of G times this, let's say these are the coefficients, let's say, for omega k on the basis Gj, okay? And so this will be now an integral weight form. And if you take an orthonormal basis for the Peterson inner product, then you get the same expression. And now this one can be generalized to the setting of rigid cocycles, because again, we do the same thing. So we take a basis for the starting space that in our case will now have a P in the level. And then omega hat, so this now again will be a finite sum. And then you have the elements of the basis tensor. Now what we have here, these are certain rigid cocycles. So this will be some finite sum, and you have the basis tensor some rigid cocycles. And so again, if you want to do rigid Shimura of G, so G, again, you write it on the basis, some scalars times the basis, and then you send it to the scalars time, and now times these rigid cocycles. So in total, this finite sum will be a rigid cocycle. Okay, and so this is how we construct the Shimura lift in this rigid analytic setting. Now, so the work that I want to present today goes in the opposite direction. So in the literature, there is the classical Shintani lift, which goes from integral weight forms to half integral weight forms. And today we're going to go from rigid analytic cocycles to half integral weight modular forms. And these two maps will not only be analog because of the direction in which they go, but also because of the construction that they have, which the construction of the two are similar. And we see that, I mean, in all the works that we presented so far, the cocycles were always playing the role of modular forms. So it seems that they might be some analogs from modular forms. And again, this belongs to the triadic program, as we will build a generating series from rigid cocycles. And in general, this work suggests some parallels between the two worlds. But now I want to give the main statement, but in order to give the main statement, I need some notation, and in particular, I need to define the rigid analytic cocycles. So there's a bit of stuff going on in this definition, so let me explain all the notation. So these are k is an integer, and these cocycles will have weight 2k. Actually, there should be a 2 here. Anyway, and they will be modular symbols. These are modular symbols invariant for a certain group, which is defined here, with values, and this is a certain space of functions on HP. So A to K, these are the weight 2K rigid analytic functions on HP. So these rigid analytic functions are just an analog of the usual holomorphic functions on the usual upper half plane. And what does it mean weight 2K? So this group gamma, SL2Z of 1 over P, is acting on HP by Mobius transformations in the same way that SL2Z was acting on the usual upper half plane. And in the same way that SL2Z had the weight 2K action on holomorphic functions, now this gamma has a weight 2K action on these rigid analytic functions, and it's defined in the same way as the usual one, okay? So that's what, so A to K are these analytic functions with this weight 2K action. And so then we take modular symbols, which are functions on pairs of cusps, with values here, and they must have some invariance property for gamma. So now, originally, these rigid cocycles were actually defined as actual cocycles in the H1, in the group cohomology, okay, H1 of gamma with values in A to K. But indeed, the group cohomology, because they were in the parabolic cohomology, so the parabolic cohomology of gamma with values in A to K is exactly the same as this space of modular symbols, which are gamma invariant in this case. So we use modular symbols because they're easier to deal with than actual cocycles in the cohomology. So now in order to state the main theorem, I need to introduce some notation. So there is a residue map, the so-called residue map, which goes from rigid cocycles to, now these are modular symbols, which are invariant for another group. And now this is the space of polynomials, homogeneous polynomials with this degree. Now, notice that this space is the space where, if you take the Eichler-Shimura isomorphism, and then you take cut forms of level P, so this group, then the space of their periods ends up exactly here with the Eichler-Shimura isomorphism, because it ends up in the H1 parabolic of gamma naught of P with values and polynomials, which is exactly this space. So this is the space of the periods, where the periods of modular of cusp forms of level P end up. And for rigid cocycles, the residues are given like this. So if you have a cocycle J, which is a modular symbol, so modular symbol means you can evaluate that a pair of cusps RS, then you send it in another modular symbol with RS. But now the image, so you take the residues of analytic functions, because JRS will be an analytic function. And then you take the residues, so there's a way to define residues on the p-adic upper plane. And then you end up, actually, you end up with polynomials if you take the residues, a bit like when you take the period polynomials of modular forms. And then so you end up with a modular symbol with values in polynomials. So now what I want to do is to plug in into this residue a certain special R and S pair. So, and this will be, this special pair will be the endpoints of the Shintani cycle attached to a binary quadratic form. So basically, there's a certain set of binary quadratic forms that was already considered by Shintani, and we're not going to define it here. But then using them, you can define the Shintani cycle, which is a geodesic in the usual upper half plane. So this is the usual upper half plane. But the endpoints of this geodesic are in P1 of Q. And so we can plug them in at in the place of RS. So we can put these endpoints RQ, SQ here, and then we get a polynomial attached to a rigid cocycle. So because if you plug in R and S, you just get a polynomial. And so this polynomial will denote it by HJQ of XY polynomial. Okay, so for any cocycle, rigid cocycle, and any binary quadratic form in this space, then okay, you get a polynomial by taking the residues of the cocycle and fixing the pair of cusps, which must be the endpoints of the Shintani cycle of Q. So this at the end will be a polynomial attached to J and Q. Okay, so finally I can state the main result. So we have a map from rigid Shintani from rigid analytic cocycles to half integral weight modular forms. It's given like this. So this is an infinite sum over, so this would actually be the set FP that I mentioned before of binary quadratic forms. Actually, we are summing over the representatives, but anyway, this is an infinite sum ranging over some binary quadratic forms. And D of Q is the discriminant of these forms. So this is a Q series. And the discriminant, you can see that is divisible by P. So this is Q to some integer. Okay, so this is a Q series, and this stuff in the angle brackets, this stuff is a number, this is the coefficient. And so we have Q to an exponent, which it depends, it's given by the discriminant of the binary quadratic form. And the coefficient is the pairing between the polynomial defined in the previous slide and the polynomial, which is the binary quadratic form. So remember, given a binary quadratic form in this set and a cocycle, we got this polynomial h of JQ. And then now we pair it with the actual binary quadratic form, and so we get the number. Now, if you define Hecke operators for rigid cocycles, you can see also that it has a Hecke invariant property, this rigid Shintani map, away from P. Now I want to compare this statement with the statement for the Shintani lift. So in the case of Shintani, the map is going from integral weight modular forms to half integral weight modular forms. And again, we are summing over the same set. So again, we have this representative. So again, this is an infinite sum over binary quadratic forms. And again, this is the Q series, and the discriminant of the form is the same, so it's divisible by P. But now the number, so the coefficient is given by integrating over the Shintani cycle CQ, okay? And then you integrate the form that you start with, which was here, times the binary quadratic form. So then one might think that, okay, so it might not be clear immediately the relationship between this number, this coefficient, and this one, and I want to compare them in the next slide. Also, I didn't write it, but also for the Shintani lift, we have the same Eke equivalence property that we have for the rigid Shintani one. Okay. So now I want to compare these two coefficients. Okay. Now remember that here we are integrating on the Shintani cycle, while here to get this polynomial, we plugged in the endpoints of the Shintani cycle in the residues of J. So now the integral is actually similar to what we did to get the polynomial H, because the integral, you can rewrite it as the pairing between Q and okay, this would be the period polynomial of the modular form F. So because the period of F is, we are seeing it as a modular symbol, okay? It would be given by integrating between a pair of cusps. Now you choose this particular pair, which are the endpoints. They are the endpoints of the Shintani cycle, okay? And you get a specific period polynomial for the modular form F. Okay, and then you pair with Q, and you get a number, and you can see that it is equal to this integral. So you see this is the same expression. If we go back, it's the same expression that we have here, because again, we are pairing with Q, which we are also doing here. And then this period of F, and you plug in RQ is the same as this polynomial, because if we go back, remember this polynomial was the residue of J. So instead of period of the form, we have the residue of the cocycle. And then you plug in the same pair, which are the endpoints of the Shintani cycle CQ attached to the binary quadratic form Q. Okay, so in our case, we would have residue of J and then same pair, and then we get a polynomial. Okay, so now I want to conclude with an example. So this rigid Shintani map, when it factors through modular forms, it factors through integral weight modular forms with the usual Shintani map. So indeed, if you recall from the beginning of the talk, remember the Zagier forms, which were the coefficients of omega k, which is the function of two variables, giving the Shimura lift. And then remember these JKDs, which were in rigid analytic cocycles, and they were the coefficients for omega hat, which is the kernel function for the, let's say, rigid analytic Shimura lift, okay? So now, so these FKDs are integral weight forms, and these JKDs are rigid analytic cocycles. So if you compute the rigid Shintani map of the rigid cocycles JKDs, this is equal to the Shintani map of the Zagier forms FKDs. I mean, actually here I am being a bit not precise, because it's not exactly FKDs, but it's some level P analog of them. Okay, because actually one can define, because these FKDs have, you know, they're for SL2Z, but you can define level P analogs of them. And again, these level P analogs will again be the coefficients of a kernel function of this form, giving a certain Shimura-like lift. And then these would be actually the forms that you would need to put here. But just to give an idea, we can think that it's these level 1 Zagier forms. Okay, yes. So I think that I will conclude here.
Yeah, thank you. Are there any questions for our speaker? Oh. It's there.
Can you hear me?
Yeah.
Hello, thanks for the interesting talk. This is a somewhat ignorant question. Supposing you replace SL2Z with the units in a quaternion algebra, you know, there's a whole family of compact quotients that you get, and I don't even know if there is such a thing as a Shintani lift. in that setting?
Yeah, I don't know either.
Okay. Thank you.
The boundaries. Find modular symbols. Yeah, I don't know. I had a question too. So the what can you say about the real multiplication values for these for the modular symbol cocycles? Is there do you know what there
Yes.
are? Are there any is there any relationship to zeta functions? Yeah.
So actually, so far they're not even well defined. And in our work with Nike Vatsal from UBC, we are trying to define the RM value of these cocycles, because if you use the same definition that you would normally use for the rigid meromorphic ones, it's not well defined, because it's not, the difference is not only that they're analytic, it's also that they're additive and of higher weight with respect to the ones which were actually evaluated by Darmon and Vonk, which were multiplicative weight 0. And the same definition does not work. And so we are actually working on actually defining the RM value. Yeah.
Okay, thanks. All right. So let's thank Isabella again.